Happy Monday. The following Zoom session is being recorded and will appear later today on my YouTube channel, Math with Mayo. There are two different classes that may be observing this session. Therefore, when you participate in the Zoom meeting, if you do not wish for your picture or your name to be made public, please leave the video off and use an alias name. If you have questions during the meeting but do not wish to speak, email me at bmayo@ybcc.edu and I'll respond as soon as I can. All right, so today we're going to start the final chapter for this quarter, chapter 11, and that will lead us right up to, we'll have our chapter 11 test on Tuesday, a week from today, and then Wednesday, Thursday, Friday, we're off for Thanksgiving break. We'll come back the last week of the quarter and we'll spend that time reviewing. But anyway, let's go ahead and take a look at section 11.3. To do that, I'm going to switch screens, so give me a minute here. Okay. All right. And okay. Can everybody see the graphing screen? Just want to make sure I've got that up there correctly. Somebody just let me know.
Yep.
Thank you. Okay. So in the past, we have looked at, for instance, linear equations. Here's an example, y equals 2x. And that looks like, let's see, it looks like this. Let's find here. So there's an example of a linear equation. It's a straight line, okay? And then we've looked at quadratic or secondary equations, y equals x squared. And that is a parabola. Today, we're going to look at yet another set of functions and equations called exponential equations, exponential functions. And they, in general, are in the form of f of x equals b to the x power, or y equals b to the x. For example, y equals 2 to the x power. Notice in this particular case, the variable is not the base, but rather it is the exponent. So let's see what we get when we make a table of values. As I've done in the past, when I'm exploring a new kind of equation or a new kind of function, I start with ordered pairs with x values going from -3 to +3. So let's see what happens there. When x is -3, we have y equals 2 to the -3 power. Recall that we can rewrite that with a positive exponent by writing 1 over 2 to the +3 power, which becomes 1 over 8, or 1/8. Any questions about how I got that? All right. If x is -2, y equals 2 to the -2 power, which is 1 over 2 to the +2 power, or 1/4. When x is -1, y equals 2 to the -1 power, which is 1 over 2 to the +1 power, or just 1/2. When x is 0, y equals 2 to the 0 power. Recall that any base other than 0 raised to the 0 power is the number 1. And then we've got y equals 2 to the 1 power, which is 2. Y equals, 2 to the 2 power, which is 4. and y equals 2 to the third power, which is 8. Now, unlike a parabola where there's some symmetry going on, here we don't have symmetry, but we have sort of reciprocals. Look here, these are reciprocals, and these are reciprocals, and these are reciprocals. All right, let's plot these points and see what the graph looks like. 5, 10, 5, -5, -5. When x is -3, y is 1/8. So that's very close to the x-axis. When x is -2, we're up to 1/4. When x is -1, we're up to 1/2. When x is 0, y is 1. When x is 1, y is 2. When x is 2, y is 4. And when x is 3, y is all the way up here at 8. So let's see what that graph looks like. It sort of looks like half of a parabola, but it really isn't. As we go to the right, this thing is going to continue to climb. As we go to the left, this is going to get closer and closer to the x-axis. But notice here, if we went -4, it would be -1/16, and -5, 1/32, and -6, 1/64. In other words, this thing would get closer and closer and closer to the x-axis, but it would never reach it. Okay. The domain of this thing, let's see. This goes on forever in this direction. This goes up and over. So the domain would be all real numbers. The range would be what? Greater than 0 on up to infinity. And let's see, it would have a y-intercept at what, 0, 1, and no x-intercepts. We also say that this thing is increasing over its entire domain. My writing is just atrocious this morning. Anyway, it's increasing over its entire domain. We're going to look at some more examples of this. Let's see. Let's do this. Let's take a look at y equals 3 to the x. Oh, you know what? I want to go back for a minute, just for a minute. What's happening to the y values as x is increasing by 1? Can you see that the y values are doubling each time x increases? 2 times an eighth is a fourth, 2 times a fourth is a half, 2 times a half is 1, etc., etc. So the base is 2. Every time x increases by 1, the y value doubles. So what's going to happen here? Well, -3, -2, -1, 0, 1, 2, and 3. If x is -3, y equals 3 to the -3 power, which is 1/3 cubed, which is 1/27th. When x is -2, y equals 3 to the -2 power, which is 1/3 squared, which is 1/9. When x is -1, y equals 3 to the -1 power, which is 1/3 to the +1, which is 1/3. When x is 0, y equals 3 to the 0 power, which is 1. When x is 1, y equals 3 to the 1, which is 3. Then we get y equals what? 3 squared, which is 9. Y equals 3 cubed is 27. Again, we get that reciprocal situation. These y values, instead of doubling, they are tripling. So we've got, let's see, -3 is 1/27th, -2 is 1/9, -1 is 1/3, 0 is at 1, 1 is at 3, 2 goes to 9. What's the domain? All real numbers, same as before. What's the range? Greater than 0, same as before. What's the y-intercept? 0, 1, same as before. What are the x-intercepts? There are none, same as before. We say this thing is increasing over its entire domain because it's going up as it goes to the right. So all that basic information is just like that. Looks very similar. The difference is it's climbing steeper. Whereas if we had, let's see, the other one kind of looked like that. Okay. So y equals 5 to the x. What's that going to look like? Well, it's going to have all the same characteristics as before, but then it's going to climb even steeper. So each time x increases by 1, y would be raised or would be multiplied by 5. Okay. So let's take a look now at, let's do this. Hang on. Let's take a look at y equals 2 to the x plus 1. What is that going to do to, where did it go here? Did I delete it? I sure did. Okay. All right. Let's do this. Apparently I'm having a Monday. Surprise. Let's go back to y equals 2 to the x. Okay, and this was 1/8, 1/4, 1/2, 0, not 0, 1, 1/2, 1/4. That's not true either. I'm definitely having a Monday. All right, let's see here. This is 1, 2, 4, and 8, and our graph 1/8, 1/4, 1/2, 1, 2, 4, and 8. So this was the graph of 2 to the x. What about the graph of y equals 2 to the x and then plus 1 out at the end there? What's that going to look like? Wouldn't that just increase all of those values by 1? So this would be 1 1/8, 1 1/4, 1 1/2, 2, 3, 5, 9. Okay. So what would our graph over here look like? Everything would be moved up 1 unit. Let's switch over to a different color. Let's make it red. So this is y equals 2 to the x plus 1. And that's going to be up there and there and there and there and there and there and there. So it's going to look like that. Remember how with the parabolas, y equals x squared, then y equals x squared plus 1, moved up a unit, y equals x squared minus 2, you move down 2 units. So this moves up 1 unit from that. What about y equals 2 to the x minus 4? That would move everybody down 4 units. Okay. Now, let's see here. Let's do this. Suppose I've got y equals 2 to the x, again, -3, 1/8, -2, 1/4, -1, 1/2, 0, 1, 1, 2, 2, 4, 3, 8. Okay, and again, I've got this graph. Looks like that. Now, as the base got larger, 3 to the x, 4 to the x, 5 to the x, this thing it climbed steeper, faster. What about this? Y equals 1/2 to the x power. Now, it's not that, because there your x, your variable, would only be on the numerator. So it's got to be like this so it applies to the whole thing. What's that going to look like? Yeah. Let's see, -3, -2, -1, 0, 1, 2, 3. Okay, so if x is -3, we'd have y equals 1/2 to the -3 power, which is the reciprocal raised to the +3 power, which is 8. If x is -2, y equals 1/2 to the -2 power, which is the reciprocal 2/1 to the +2, which is 4. Y equals 1/2 to the -1 power is 2/1 to the +1 power, which is 2. What's halving? What's happening here? It's halving, isn't it? So this would be what? 1, a half, a fourth, an eighth. And the graph, instead of looking like the y equals 2 to the x, where it's increasing, it's going to look like this, roughly, and it's decreasing. It still has a domain of all real numbers, a range greater than 0, a y-intercept of 0, 1, no x-intercepts, but now it's decreasing. So what we get is this: if we've got y equals b to the x, if b is greater than 0, no, that's not true. If b is greater than 1, we get this thing that increases. If b is between 0 and 1, we get this graph that decreases. What about if b is 1? What does that look like? Well, hey, well, let's just do this. Let's erase this. And if b is just 1, so y equals 1 to the x. -3, -2, -1, 0, 1, 2, and 3. Well, what's 1 to the -3 power? It's 1/1 cubed, which is 1/1, which is 1. What's 1 to the -2 power? It's 1/1 to the 2 power, which is 1/1, which is 1. And we're going to see that we get this, which would just be a constant function, a constant equation. That doesn't behave like the rest of those things. So what we say is, let's go back here. Can you see this information, or is it covered up by the people on the screen? Anybody?
Can mostly see it.
Mostly is not good enough. So let's do this. Let's go start over and say, okay, if we have y equals b to the x, b cannot equal 1. If b is greater than 1, the graph increases. If b is less than 1 but greater than 0, the graph decreases. Okay. The domain is all real numbers. The range is greater than 0. There's no x-intercepts, and the y-intercept is at 0, 1. That's for all of them of this form. Okay. Now, what about y equals b to the x, where b is a negative number? Okay. I'm not going to spend a lot of time looking at that, other than to say, if you try to graph it, you can't graph it because the dots are all over the place. In fact, it just, yeah, it doesn't happen. So b has to be greater than 0, but not equal to 1. If b, that base, is between 0 and 1, it's going to decrease. If it's greater than 1, it's going to increase. All right. And all of that information is on page 926 of the hardcover book. I'm not sure what page that would be on if you have the loose leaf copy. But anyway, any questions about that before we go on? All right. What I want to look at now is let me get, let's see, I'm going to actually switch screens. Go back to the regular screen. And we'll start the share. Okay. So now you're back where you can see my whiteboard screen. I'll take that as a yes.
Yes.
All right, so let's say we've got this. It says A equals 500 times 2/3 to the t power, okay? Now, this is sort of like y equals a times b to the x. In other words, this is the base of the exponential part of the equation. This is a constant multiplier out front, okay? So my question is this. This equation, if t stands for time, is this thing going to increase over time or decrease over time? What do you think? Is it going to increase or decrease? It's going to decrease because the base is between 0 and 1. Okay, remember a graph that's greater than 1 looks like that. Between 0 and 1 looks like that. So it's going to decrease. Second question, what is the starting amount? In other words, when t is 0, what is the value of a?
0.
Careful. What's 2/3 to the 0 power equal to?
Oh, 500.
Right, but to answer that last question, 1, so then 500 times 1, right.
Yes.
So what we've got here, we've got an equation where the starting value is 500 and it's decreasing from there. Now let me read you the actual problem. It says 500 grams of a radioactive material decays according to this formula, where t is measured in years. Find the amount present in 10 years, round to the nearest 1/10 of a gram. Okay, so they just restated what we already determined. There's a starting amount of 500 grams, okay? It's decaying because the base, 2/3, is between 0 and 1. They want to know, since t is time in years, find the amount present in 10 years. In fact, let's rewrite this as a function using function notation. So a of 10 would be 500 times 2/3 raised to the 10th power. So on my calculator, 500 parentheses 2 divided by 3 close parentheses to the 10th power. So this is what I wrote on my calculator. 500 parentheses 2 divided by 3 close parentheses to the 10th power equals, and it said round to nearest 1/10 of a gram, and I get 8.67. This is the 10th column, the 7 would round up, so 8.7 grams. So we started out with 500 grams. It's at the end of 10 years, it has 8.7 grams of some radioactive material. Okay with that? But again, here's our starting value, and this is a decreasing function because the base is between 0 and 1. Okay, how about this example? P equals 3,745 times 0.93 to the t power. At the beginning of time, so time here, or T stands for time in years, and P stands for population. So at the beginning of time, what's the population of this particular example? Anybody? So when T is 0, what does P equal?
3,745.
Right, it's just like the previous problem. Is the population growing or decaying?
Decaying.
How do you know?
It's less than 1. The base is less than 1.
Right. Now the double jeopardy question, and be careful. By what percent is the population decreasing every year? Careful.
Is it 7%?
Good job. You get a
Yay.
gold star here. Well, yellow anyway. Good job. Yes. And if you're sitting there going, where did she get that? Well, every time T increases, we have 93% of what we did have. So we're losing 7%. Excellent. Now, this is what it says. The population of North Rivers is decreasing exponentially according to the formula, where T is measured in years from the present date. Find the population in 6 years, 9 months. And again, I'm going to put it in function notation. Okay. So if T is measured in years, 6 years, 9 months, careful. How would you write that in years? It'd be 6 point what? 9 months is what fraction of a year?
3/4.
So what would that be as a decimal?
0.75.
Good job. So P of 6.75 equals 3,745 times 0.93 raised to the 6.75 power. So 3,745 parentheses 0.93 close parentheses raised to the 6.75 power. And let's see, does it say anything about rounding? They round to the nearest person, and what we get is 2,294.62502. So this would be the whole number. This would round up, so 2,295. So the population would decrease down to that. Okay, any questions about that? Have you ever heard on the news or read in the newspaper where it makes some reference to something? It'll say, and something is increasing exponentially, or it's decreasing exponentially. This is what's going on. These are exponential equations. Sometimes it's used correctly. Sometimes it's used where it's like, I'm not sure that it's being correct. But anyway, the idea of exponential growth and exponential decay is going to be one of the main themes of this chapter. Now, there's a formula, and I'm going to write it down here as soon as I find it. Here it is. It says A equals P times the quantity 1 plus R over K, all raised to the KT power. All right. This is the formula for compound interest. So if you took Math 75 pre-algebra, you would have studied simple interest, which is, let's see, I equals PRT, okay? This is compound interest. So what happens is you let's say you put some money in the bank, and at the end of some time, they pay you some interest, and the interest stays in the bank. So then for the next period of time, you're not only getting that original interest again, but you're getting interest on the interest, and that goes back in the bank, and it just keeps compounding. You get interest on the interest on the interest on the interest, etc. Okay. When you're investing, compound interest is good. When you're paying off a loan, compound interest is not good. P is the principal. Okay, R is the annual interest. Interest rate. T is time in years. And let's see here. Oh, A is, I'm going to say the accumulated amount. Now, K is the number of compoundings per year. Okay, so if interest is compounded annually, that's once a year, K is 1. If it's compounded semi-annually, that's twice, K is 2. If it's compounded quarterly, that's 4 times a year, K is 4. Monthly, K would be 12. Daily, K would be 365. All right, now, here is a problem. It says compound interest. An initial deposit of $10,000 earns 8% interest compounded quarterly. How much will be in the account after 10 years? So using the formula, A equals P times 1 plus R divided by K, all to the KT power. An initial deposit of $10,000, so P is $10,000, earns 8% interest. R is 8%, which we would convert into a decimal number. Compounded quarterly, so K is 4 times a year. How much will be in the account? So that's our unknown after 10 years. Okay, so we know everything except A. So A equals 10,000 parentheses 1 plus 0.08 divided by 4, all raised to the 4 times 10 years. Excuse me a second here. All that wind kicks up my allergies. All right. Now, we can do this a couple of different ways. We can do some simplification ahead of time. We can take 10 times 4 and turn it into 40. We can take 0.08 and divide it by 4 and then add the result to 1. Okay, and that's all great as long as you don't have to do any approximating. Let's say, for instance, we had 0.08 divided by 3. That does not come out nicely. If you get something like that, you need to just leave it alone, punch it all into your calculator, and then round off after you get your very end results. Okay. So, for example, this one, I could do this. 0.08 divided by 4 is 0.02, and 4 times 10 is 40. Okay. I could further write it like this. So I got 10,000 times 1.02 to the 40th power. And I could put that all into my calculator. 10,000 parentheses 1.02 close parentheses raised to the 40th power. And I get 22080.39664. This is money. Let's see. It doesn't say anything about rounding, but since it's money, we'd round to the nearest cent, which would be there. So this would round up. So $22,080.40 would be the final amount. Okay. Now, I could also just put this into the calculator as it is. And let's look at what that would look like in the calculator. Okay, so you'd have 10,000 parentheses 1 plus 0.08 divided by 4, but you're only dividing the 0.08 divided by 4. Close the parentheses, the little caret power key, and then parentheses 4 times 10, close parentheses. Okay, so if you don't pre-multiply the 4 times 10 and make it 40, you need to put parentheses around that whole thing. Otherwise, it's going to think it's raised to the 4th power, and then that whole result times 10. So you've got to tell the calculator that that 10 is part of that exponent. Okay, so make sure you're getting the same answer that way. Here's another example. It says, how much more interest could $1,000 earn in 5 years compounded quarterly if the annual interest rate were 5.5% instead of 5%? So what we're looking at here is, how does having a slightly different interest rate affect the outcome? So our formula, A equals P times 1 plus R over K to the KT power. And let's see. In both cases, the principal is $1,000. The time is 5 years. The compoundings quarterly, so that's 4. Now, what changes the annual interest rate? So here it's 5%, which is 0.05. Here it's 5.5%, which is 5.5%, which is 0.055. Okay, so we've got that extra 5 out here because it's a slightly higher rate. So A equals $1,000 times 1 plus 0.05 over 4, close it up, to the 4 times 5 power. Okay, 1,000 parentheses 1 plus 0.05 divided by 4, close that whole thing up, raise it to the power parentheses 4 times 5, and I get 1,282.037. So $1,282.04. Okay, then over here, A equals $1,000 times 1 plus 0.055 over 4 raised to the 4 times 5 power. Okay, so 1,000 parentheses 1 plus 0.055 divided by 4, close it up, raise it to the parentheses 4 times 5 power, and I get 1,314.066. So that would be $1,314.07. And it said, how much more interest? So I'm going to take 1314.07 minus 1282.04, and I get $32.03. Now, that may not seem like much over 5 years, but it's the same amount invested. It's just sitting there, not doing, in their bank or whatever institution, but having a 0.5% more in interest rate, you get $32.03 more. So if everything else is equal and you've got 2 different potential investments, the one that pays the higher interest rate would be the better one. Now, the reality of it is that when you're investing like this, and it's not just, say, a savings account, there might be an investment that promises a higher interest rate, but also has a greater risk. So you might think, well, why not just always invest at the higher rate? Often some investment that says, oh, we think you'll get 10% return, or you might lose it all. Anyway, welcome to the stock market. Okay, let's see here. One more example. If $1 had been invested on July 4th, 1776 at 5% interest, compounded annually, What would it be worth on July 4th, 2076? Okay, so A equals P times 1 plus R over K to the KT power. Principal is $1. The interest rate is 5% or 0.05. K, it says annually, is so one time from 1776, from July 4th, 1776 to July 4th, 2076 would be 300 years, right? 17, yeah, 300 years. Okay, so A equals $1 times 1 plus 0.05 divided by 1 raised to the 1 times 300 years, which would be $1 times 1.05 to the 300th power. Do you see how I got that? This is just going to be 0.05 added to 1.05, and 300 times 1 is 300. So I can simplify that quite easily before I put it into the calculator. 1 times parentheses 1.05 raised to the 300th power. And this is what I get. 227,399,6129. That's going to round up. So 227,399,6.13. $2,273,996.13. If only we'd been there and could have invested that much. All right. So for tonight, you've got section 11.3, exponential functions. You're going to use this formula for compound interest situations. And I will be back at 1:15 with an office hour should you have any questions. Otherwise, have a great rest of the day, and we'll see you all later.